So there are more applications for simple harmonic motion than just a spring bouncing back and forth on a shuttle or whatever. And so we want to talk about those in Young and Freedman in their University Physics 2 in Chapter 13, the fourth section. So for example, simple harmonic motion can occur not just in a horizontal boing, 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 but also when you have a vertical boing, 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 boing. Anytime when a restoring force is proportional to the displacement, the restoring force being like the spring pulling it back to equilibrium, whenever this restoring force is proportional to displacement, you have simple harmonic motion. So here's a diagram having to do with vertical simple harmonic motion. So you have some sort of mass suspended on a spring. So delta L here is the displacement from what the spring, if the spring didn't have the mass on it, what its equilibrium point would be. And then when you put the mass on it, it extends to a new equilibrium point with the mass. And delta L is the difference between the equilibrium point of the spring by itself and the equilibrium point of the mass on the spring. You basically, what is the force that is extending that mass? Well, it's the force of gravity, which is mg. And so the spring constant times that change in L, Fx, is going to equal the force of gravity, mg. And then we're going to say x is 0. And basically, all the things that have applied for simple harmonic motion on a horizontal shuttle bouncing back and forth on a spring are going to be true of a mass hanging from a spring. So the restoring force is going to equal negative kx, where x is wherever it is from the mass plus spring equilibrium point. The angular frequency is still going to be the square root of the spring constant divided by the mass, k over m, square root of k over m. The frequency is still going to be the angular frequency divided by 2 pi. So 1 over 2 pi times the square root of k over n. And of course the frequency is the opposite of the period. Frequency is cycles per second, and the period is seconds per cycle. So you just flip everything. So it's 2 pi times the square root of m over k. Again, this is all the same as when we had a horizontal simple harmonic motion. There's also something called angular harmonic motion. If you're wondering what this crazy looking contraption is, this is a spring that is might be used in a mechanical watch. So you have the balance spring and the balance circle. This is the balance spring, and then this is the balance circle. And so basically the spring is wound in such a way, out of such a material, at such a, in such a way that when it begins, when you wind it up and it begins to, it basically is boing, 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 and this goes tick tock, tick tock, tick tock, as the angular harmonic motion, boing, 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 is created. This is the way mechanical watches used to work. How brilliant the inventors of these were. So angular simple harmonic motion, that's my bad drawing here, but you basically have the instead of x you have theta, an angular displacement, and instead of F you have a restoring torque. So instead of a restoring force, you have a restoring torque, where torque is basically force as it relates to angular kinds of things. And these formulas look a little bit different, but they're basically just angular versions of what we had for the spring. So instead of F equals negative kx, we have torque, which is like F, equals negative kappa, where kappa is the constant in terms of angular constant, as it were. And then instead of x, we have theta, which is the displacement angularly. I'm sorry, it's called the torsion constant, this kappa here, which is like k, the spring constant. So omega is still the angular frequency, and instead of it being the square root of k over m, it's going to be the square root of kappa, the torsion constant, over I, the moment of inertia. Again, if you've been following along in this sequence, you find that the moment of inertia often replaces the mass in formulas. It's pretty much an exact equivalent. The moment of inertia basically has to do with more complicated structures. So the frequency, again, is going to divide the angular frequency by 2 pi, and you end up with the frequency in hertz, cycles per second. And so divide by 2 pi, and then kappa over I again. And the period is again going to be the frequency flipped. So instead of 1 over 2 pi, it's 2 pi. And instead of the square root of kappa over kappa over I, it's going to be the square root of I over kappa. Again, it's pretty much exactly the same, just with the equivalent angular kinds of things. So you might remember when we were talking about simple harmonic motion, there was a formula, x equals amplitude cosine of omega t plus phi, where phi is the phase angle, angular frequency, time, and so forth. Well, basically, this is just the angular equivalent. So instead of x, we have theta. And instead of a for amplitude, we have big theta, which is this is a small theta, a lowercase theta, as it were. This is an uppercase theta. I know I didn't draw it really great, but you get the picture. And so the big theta, uppercase theta, is the equivalent of the amplitude in the other formula. Again, nothing, it's just the equivalent of what we've done using angular, the relevant correlates in angular considerations. He does end with an advanced section on the vibration of molecules. There's something in chemistry called van der Waals forces that apparently involve the kind of very minute vibrations of two atoms that are connected to each other. Again, the math goes a little bit beyond what they can expect even a calculus student necessarily to fully do. It involves the binomial theorem, for example, and I have a video on that that will be linked to this somewhere. So capital R0 is the equilibrium point. That is when these molecules are the repulsion and attraction forces when they're equal in equilibrium. That's R0. But there can be some, because of van der Waals forces, there can be some vibration of molecules so that the R is either a little bit more than R0 or the R is a little bit less than R0 between atom 1 and atom 2 in a molecule. He gives you the formula, and again, I think you should be in awe of the formulas, but probably a beginning calculus student is not expected to be able to do all the things he shows you. Basically, as it turns out, he does some work there on potential energy and so forth, and the end result is that the restoring force with regard to these two atoms is going to equal negative times 72 potential energy O over the equilibrium point squared times x. Well, basically he says, look, this is, since 72 capital UO over RO squared, that's basically a constant. And so, more or less, this is in the form of F equals negative kx. When the amplitude is very small, that is, when the vibration amplitude change is very small in relation to the equilibrium distance between the centers of the two atoms, and when that distance divided by, well, basically, that's saying the same thing, when the variation between the molecules divided by the equilibrium distance is much smaller than 1, that's what that means, much smaller than 1, then this would be true. Well, in other words, it turns out to be harmonic motion going on between two atoms. I think mostly this is just for fun, not something that you would need to know much about unless you were moving on to do advanced physical chemistry. Okay, thank you.